Okay, everyone. So we're going to continue with a little bit of topology today. This, depending on how far we get, this could get a little hairy, just kind of as a heads up. But let's see. Let's see what happens. I think, from last time, there was a lot of good engagement. People were asking lots of great questions. It was a lot of fun. So let's kind of see where we end up. So to recall, we talked about open sets. We talked about closed sets, remember? And so a set is open if all of its points are interior points. And what does it mean to be an interior point? It means that you can put a little ball around your point that stays entirely within your set. And then you're closed if your complement is open, right? So that's the definition. Now, one of the problems with the definition of closed, right? So you're closed if your complement is open, that's not really usable. That turns out to be pretty intractable because you think about what you'd have to do. So you have to take your set, you have to take its complement, then you have to prove that its complement is open, and all of that just gets to the fact that the set is closed. So it'd be nice if we had some sort of criteria that we could immediately use and just be like, oh, look, if this is true, then my set is closed, right? Without having to take complements and check if that's open, if that makes sense, right? Like we don't want to have to try and prove closedness through some other property. Now, if you have been following along, right, one of the other things we talked about were boundary points. And boundary points were these things that, as the name describes, kind of sit at the edge of your set, right? Maybe we could even like draw a little picture here. We're just on the real line, right? And maybe here's our set S. And so, everything in here, this is all interior points. And then these two things out here are boundary points. And it feels, I think, probably intuitively, right? So the definition, maybe let's say this first. The definition of a boundary point is that no matter what ball you put around it, that ball intersects both the original set that you were in and the complement of the set. And you can see that that's going to happen at these points, because if I take this point here on the right-hand side and draw a little ball around it, yeah, no matter what size ball I draw, part of it is going to be in the set, part of it is going to be outside of the set, right? That's a boundary point. So it feels as though boundary points tell you something about closedness, i.e. maybe if you have all of your boundary points, then you're a closed set, right? Yeah, well, exactly like superinfs. So superinfs are always boundaries, that's for sure. But we have to be a little bit careful, because it is possible for, this brings up kind of a great point. It is possible for the superinf to not exhaust the boundary points, right? So we could have something weird, like where I give you maybe two intervals like this, right? Like maybe that's the set S. Well, then the superinf, right? This is the inf here, and the sup's up here. But there's two more boundary points as well, right? So the inf and sup are definitely boundary points, but there could be more boundary points, right? And we saw that when we talked about like the rationals yesterday as well, because we said the boundary of the rationals were all the real numbers, but they don't actually, the rationals don't have a superinf because they're not bounded. So like superinf, definitely that's a great way of thinking about it. That's a really, really good way of thinking about it. But as long as we just kind of keep in mind that there could be more things that kind of behave like that, right? Okay, so we kind of have, I hope, this feeling that if a set contains all of its boundary points, then it's actually closed. And that turns out to be correct. So proposition. So a set S is closed. And again, we already have that definition of closed, right? Its complement is open. Its set is closed if and only if the boundary of S is contained in S. It has all of its boundary points, right? Because the boundary point doesn't need to be part of the set, right? You can talk about a boundary points if it's an open interval, the boundary points are its endpoints, but the endpoints aren't actually in the set. So a set is closed if and only if it has all of its boundary points. Okay, now this proof, and unfortunately most proofs like this are kind of right only in the sense that they get a little bit hard to follow because notationally just things are all over the place. So that's just kind of unfortunately how these things go. And I am tempted to give you a shot at this first. Maybe let me do one direction and then I'll give you a shot for the other direction. So let's do this direction. So suppose that S is closed. Okay, so I want to show that all of its boundary points live inside of it. So what I'm going to do for this question is I'm going to assume for the sake of contradiction, it's not true. for a contradiction. These proofs especially often have many, many different types of proofs. This is the one that I chose because it was just, to me, what was intuitively obvious. For a contradiction, suppose we can find a boundary point which is in the boundary, but not in the set itself, right? That's because that's what the negation of the right-hand side is, right? The boundary is not inside of S, so there must be some point which is in the boundary, but not in S. And of course, it's hard to get, again, an intuition for this sort of scenario because we're in contradiction land, right? Everything's going to be nonsense. But basically what I want to say is the following. Well, look, if X is in the boundary point, is in the boundary, but not S, two things happen. The first thing, X is not in S, which means it's in its complement, right? Maybe let me kind of write that out in not bullet point, but so we get two things here. So since X is in the boundary of S, what does that mean? That means that for every R greater than 0, BRX intersect S is not empty, right? That's part of the definition. And BRX intersect the complement is not empty, right? So that's what it means to be in the boundary point. But two, we also have that X is not in S, right? That's what we did. We said X is in the boundary, but it's not in S. So in particular, it has to be in the complement. But the complement is open, right? Because we assume that S is closed. So that means there exists some R greater than 0, such that BR, maybe let me call it BR hat, just so we don't confuse it with the R's above. So that also has to be true, right? And we're very quickly going to see the contradiction because in number 1, it says that this has to be true for all radii, right? No matter what ball I impose, has to be contained, has to intersect both S and the complement set non-emptily. But property number 2 says that there's some ball that I can impose that doesn't leave the complement, right? Namely, it doesn't hit S at all. And that's a contradiction. We can't have both those things being true. So, I mean, that's kind of like the idea that's going through my head when I prove this. And so I'm going to say, you know, to do it formally. So since X is, let's say since X is in the complement, which is open as S is closed, there exists some R greater than 0 such that BRX, the open ball, contains entirely in the complement, but X is also in the boundary. So BRX must also intersect S. And that's not possible. Right, so that's a contradiction. Voila. Right, you can't both be in a set and its complement, right? Those two things, it's like P or not P, right? You're either, for every set S, at any point, you're either in the complement or you're in the set itself, because the union of those two things is your entire space, right? So I'm kind of implicitly using that, but hopefully it's okay. And so that takes care of that. Now, the other direction, yeah, I want to give you all just a little bit of shot, because I think, you know, at some point you kind of need to write down a contradiction. Need to write down a topological proof. I will say just kind of ahead of time, I didn't do this one by contradiction. I did this one by contrapositive, but there's no reason saying that you have to do it that way. So I want to give you a couple minutes just to throw your hat in the ring and see if you can come up with a proof for this one. So give it a shot, just spend a couple of minutes, see where we get. If you don't get anywhere, that's totally fine, right? Just see if you can use the tools that you have and get somewhere. And then, you know, if you have any questions, throw something in the chat and I can help you out there. Okay. So any progress? Does anyone think they got it? Even more boldly, does anyone think they can coach me through their answer? Again, there's definitely probably multiple ways of doing this one. And you definitely don't have to do it the way I did it. But does anyone feel confident that they got an answer? Some people actually define closed sets in this way. They define a boundary point, say a set is closed if the set contains all of its boundary points, and that's the definition, and then defines an open set as the complement of a closed set, right? So some people actually do it that way instead. Follin famously does it this way. No, that's okay. Okay, so like I said, I'm going to do it by contrapositive. And kind of the issue with these proofs, especially in this case, as I do it by contrapositive, is that there's going to be a lot of knots hanging around. So you'll see what I'm saying. So I'm going to say, assume that S is not closed. Right? That's not the same thing as saying open, right? I'm just saying it's not closed. So S is not closed. Let's show that we can find a boundary point that's not in S. So let's find an X in the boundary point that's not in S itself, right? Okay. So the fact that S is not closed means its complement is not open. So since S is not closed, SC, its complement, is not open, right? That's kind of a weird sentence, but again, the definition of closed is that your complement is open. So since S is not closed, its complement can't be open either, because if its complement was open, then S would be closed, right? So its complement is not open. In particular, that means that there exists a point some point X in the complement, which is not an interior point, right? And what is the negation of an interior point? So if you negate that definition, you get that for every R greater than 0, BR of X is not entirely contained in the complement, right? i.e., this ball has to intersect S. But does not closed equal open? No, so that's not a dumb question. And that's definitely something that people confuse all the time. Not closed is not the same thing as being open, right? So again, kind of our example here, we could have something like 0, 1, right? So this is open. And then 0 and then close 1. This is not open, right? But it's also not closed, right? So you can get these sets that are neither open nor closed, right? And then you can have like, 0, 1 is sort of closed. So yeah, it's one of these, excluded middle things, right? That there's a third possibility that could happen where not open, not closed, and then there's something in between, which is neither, right? Yeah. So, and that's just why I was being careful, right, about saying not closed, not open everywhere, rather than saying, oh, if you're not closed, then you're open. That's not true. So we just have to stick with this weird not closed, not open thing. So again, this is kind of a weird proof because it's got all the knots in it, right? It's got lots of like, I'm not in this, I'm not in this, I'm not a subset of this. But anyway, so we know that for every R, BRX is not contained within the closure. What does that mean? It means that it must intersect the complement of the complement, sorry, not the closure. If BRX is not contained in the complement of S, some of it must be in S, right? So i.e. BRX must intersect S in a non-empty way, right? And moreover, X is in the complement, so it certainly intersects the complement in a non-trivial way, right? Namely, we've shown that X is a boundary point, but X was also in the complement, so it's not an S, and we're done. Right? So this is, like I said, this is kind of a weird-ish proof, and almost certainly there are other ways of doing it. To me, this way definitely makes sense and actually really highlights something, which is namely, if you negate the definition of an interior point, you basically get a boundary point, right? Or you get an exterior point. But if you assume that you're inside of your set, if you're in your set and you're not an interior point, then you have to be a boundary point, effectively by definition. And that's kind of a nice and insightful thing that we can see. I.e., sure. Where did I put it? Oh, yeah. So my claim is that this statement and this statement is true. Okay, these are the same thing. So basically, you know that the ball is not in the complement, right? Some of it could be, but it's not entirely in there. It's not a subset. So if it's not a subset of SC, some of it must be an S, right? Because S and SC together are everything, right? S union SC must be all real numbers, right? You're either in S or you're not. So the fact that the open ball of radius R is not contained in the complement of S must mean that there's something, some part of that open ball, which is in S itself, right? Does that kind of make sense? Like some of it, you're just told it's not in the complement. Or I think part of the issue here is that I'm kind of taking the complement of the complement when I do this, right? Like here, I'm really thinking of S as being S complement, complement. Okay, so is that like if A is not a subset of B, then A must intersect the complement of B. Does that make sense? And that's what I'm using, right? So where A is the open ball and B is S complement. But the complement of the complement is the original set. Okay, so hopefully that sorts it out. Let me know though if you're still confused. And are you good with the second line? Like, are you good with this line too? All right, that one's not empty because after and right. Okay, so X itself is in here, right? It's definitely in the ball because it's the center of the ball. And if you look at what we originally assumed, X is in the complement. And so the fact that X is in the complement and in this open ball means that if I intersect it with the complement, I get something, there's not empty, right? There's something in that intersection, and namely X. X is in both of these sets, right? X is in here and X is in there. So the intersection can't be empty. Okay, cool. All right. So like I said, these proofs can be a little bit hard to read. These are definitely the proofs that I think if you spend long enough thinking about them yourself, often you can come up with them. They're kind of a little bit messy at times, but whatever, it is what it is. But when you try and write them down and show them to other people, it's very hard, just because there's a lot of notation and there's a lot of kind of baggage that comes with every single word that you write down. So it's definitely worthwhile. Now, what I think I'm going to do, I originally was thinking about proving these, but I might relegate these to, oh no, well, I have to do a definition first. So either way, let's do that. So what we're going to do, let's define this. This is very related, right? So if S is a set, the closure of S is defined to be this thing. So we're going to use a little overline here. And that's going to be S union the boundary of S. Okay. And so basically the idea of the closure is you say, well, S itself might not be closed. In particular, the thing that it might be missing is its boundary points. So what we're going to do is we're just going to throw the boundary points in, and we're going to define that to be the closure. All right. So that's kind of the idea there. We take S, we throw in the boundary points, and that's going to be the closure. And the hope is, right, we kind of hope a couple of things that we would need to prove. We hope that the closure of S is closed. And in some sense, it's the best closed thing. It should be the smallest closed set containing S, right? Like I threw in exactly what I needed to make the set closed and nothing extra. So it should be the most efficient way of producing a closed set that contains S, right? That's sort of the idea there. Okay, so I'm going to leave these. Like I said, I'd originally planned to do these, but if I really want to get into compactness, I don't think I'm going to have time. So exercise, I want you to prove the following. I'm going to use both of these. Show that the complement of the closure is the interior of the complement, right? And again, that should be sort of intuitively obvious, I hope, if you think about it. So for example, if you took something like, so let's say you took something like 0, 1, right? So the closure of 0, 1 is the closed interval 0, 1, right? Because you just throw in the boundary points. And then if you take its complement, what are you going to get? So you're going to get negative infinity to 0, union 1 to infinity, right? And okay, so that's one side of this equation, right? Let's check the other side now. So S complement, if I just did this complement, so I would have gotten negative infinity to 0, union 1, closed 1 to infinity. And so if I take the interior points of this, yeah, I'm just going to throw away the boundary points, and that gives me the same set. Right? So it does seem to kind of work out by example. Obviously, that's not a proof, right? But it does seem to work out by example. And again, if you can kind of visualize this thing, right? I close it, so I throw in the boundary points, and then I take the complement. And what you can actually what you might want to do to help you visualize this and or help you prove this is to prove that the boundary of S is the same as the boundary of its complement, right? Those two things have the exact same boundary, right? The boundary of one is the boundary of the other. So you could try that. This proof, again, is not terribly hard. It's one of these right-only proofs, though. Unfortunately, you just kind of have to do it. And you have to do 2 of them for this, right? You're trying to show these 2 sets are equal. So you need to do this through a double subset inequality. Start with an element on the left-hand side, show that it's in the right, right? Start with an element on the right, show that it's in the left. Kind of can't avoid it, but give it a shot, okay? And then the other thing that I want you to do is show that if A is a subset of B, then the closure of A is contained in the closure of B, right? Which again, I think intuitively makes sense, but you really want to prove that because you know that closures can do some weird things, right? You know, for example, that the closures of the rational numbers is all of the real numbers. And that is like, wow, that really exploded. That kind of got really big fast. And so it doesn't seem unreasonable that you could have something kind of weird like that happen, but no, closures respect the inequalities, the subsets. If A is a subset of B, then yeah, the closure of A must be a subset of the closure of B. Okay, so it respects subsets like that. That proof is, I think, actually, believe it or not, that proof I think is a little bit trickier than the first one. But again, it's not that bad in the sense that you're really just unwinding definitions, right? You're saying, what is the definition of the closure? Okay. How do I apply that, right? Start with an element of the closure of A, show that it's in the closure of B. What do you know? Oh, A is a subset of B, right? Take that and run with it. So I'm going to use both of these facts. They're just kind of fun things for you to try proving if you want to get your feet a little bit wet. And of course, you know, if you try them and you can't get anywhere, ask me about them. You know, maybe ask on Discord, ask on Piazza, whatever the case might be, you know, just give it a shot. So now that we have the closure, I want to prove the following things. So proposition, so let's say let S be a set. Okay, so number 1, the closure of S is closed. We're really hoping that was true, because if that wasn't true, that would have been weird. S is closed if and only if it's equal to its closure, right? And again, hopefully that kind of makes sense. Like the closure is you're just adding in whatever you need to make S closed. Well, if S is already closed, it should be equal to its closure, right? 3, S closure is the smallest set containing S, smallest closed set. Containing S. This might be your first time seeing this kind of used in terms of sets. Like, what does it mean to be the smallest set containing something? So let me write that out. I.e., so that is, if C is closed and S is a subset of C, then I guess this isn't the best way of saying this. Whatever, it's how I'm going to say it. Then S bar is contained in C. Okay, there's a slightly better way of saying that, but let's do it that way for now. And for the closure of S is the intersection over all closed subsets containing S. Okay. All right, so let's prove it. Now, the proof of 1 is not too bad, given that we have one of our examples or exercises from above. So we want to show that the closure of S is closed. Now, what was the last one? So the last one is that the intersection of all the closed sets containing S. Yeah, we have to kind of parse what this sentence says, right? So this says, take the set of all closed sets which contain S, right? So this is a set of sets, and every element of this set is closed and contains S. If we intersect all those things together, we get S bar, okay? All right, so we want to prove that the closure of S is closed, and again, your first instinct might be to do something like, we literally just proved that you're closed if and only if you contain your boundary points, but believe it or not, that's actually not the best way of doing this because we don't necessarily know how the boundary of the closure interacts with the boundary of S. What we do know, however, is that the complement of the closure is the interior of the complement and is therefore only has interior points. So that means that the complement of the closure is open, and hence S bar is closed. All right, okay, great. 2 is an if and only if, so we have to prove both directions here. One direction is much easier than the other. Not that either direction is particularly hard. So let's suppose that S is closed. Okay, so first of all, we already know that S is a subset of S closure, right? Right, we get that for free. Just the definition of the closure is S union the boundary points, so S must be a subset. In order to show that these two things are equal, we want to show the opposite direction, right? Since S is closed, it contains its boundary points. Right? So what does that mean? Thus, S union its boundary points, which is the same thing as the closure of S, is contained in S. Right? And therefore, these two sets are equal. Thus, S is equal to S bar. Right? That's only one direction. We have to do the other direction, but this one's trivial. Right? So we're going to assume that S is equal to S bar. We want to show that S is closed, but by 1, right? What did we prove in one? S bar is closed. S is equal to S bar. S must be closed. Right? So there's nothing to do there. Okay. So number 3. So we want to show that it's the smallest closed set, namely if C is any other closed set containing S, then S bar is contained within C. Well, this one's also pretty straightforward if we use one of the exercises that we had above, right? So suppose C is closed and S is a subset of C. Okay, so what I'm going to take is I'm going to take the closure of both sides of this subset. And I know that closures respect that subset inequality, right? So that means that S bar is a subset of C bar. But C bar is already closed. And by part 2, that must mean that C bar is equal to C. And that's what I wanted to show. S bar is contained in C, right? It is the smallest open set, which works. So I'm done. All right. And so finally, this crazy one, this one is actually, there's some way in which you could interpret 3 and 4 as being effectively the same statement. In fact, some people will say that you are the best, you're the smallest open set precisely if you are the intersection of all the things which do the thing that you want. Anyway, so let's say note that, what do I want to say? Let's say define K to be this thing, the thing that over which we're intersecting. All right, so it's the collection of all closed sets containing S. All right, so note, first of all, S bar is in there. All right, it's one of the elements of K because it's a closed set which contains S. So in particular, so S, that would tells us that the intersection over K is contained within S bar, right? Because the intersection is always smaller than any of the sets over which it's intersecting, right? A intersect B is a subset of A. A intersect B is a subset of B. So if S bar is one of these sets that we're intersecting, the intersection must be smaller than it, right? But conversely, by 3, S bar is the smallest open set. Conversely, S bar is a subset of C for all C's in K. And so it must live in the intersection. Right? Now we've proven both subsets, therefore the sets are equal. And we're done. Right, so not all the proofs have to be nasty, but again, we're, I think, very rapidly building up a toolbox, right? And a toolbox of things that we can use. And once that toolbox, as that toolbox begins to get bigger, the possible proofs that you can employ significantly increases as well, right? Things are a little bit easier when you've only got a few tools that you can use, but once you've got a lot of tools, suddenly, right, it can start to get overwhelming. And again, like I said, that's okay as well. Why is the intersection of K is a subset? Sure. So zoom in screen. Thank you. So what I'm using here is that A intersect B is always a subset of A, right? So if you're one of the intersecting sets, then you're a subset of the thing. So what I said is up here, we know that S bar is one of the things that shows up in the intersection, right? It's in the intersection on the left-hand side. And so the intersection must be a subset of S bar. No, it doesn't belong to the intersection. A might belong to its union, but the intersection belongs to A. Right? Not the other way around. The intersection is smaller. So does that clarify it? Are you okay? Right? The intersection can always get smaller because you're imposing more restrictions, right? You're saying it has to be in multiple things. Can you explain in 3 why these two statements are equivalent? So which statements are equivalent, Stephen? I'm not certain which. So in number 3, you're saying, right? Before and after that is. Oh, meant 3. Oh, I see. Okay. So in fact, oh, I see. Okay. So if that's true, these two statements are equivalent because, first of all, you can see I used 3 to prove 4. And if you have 4, 3 is automatically true, right? S bar is the intersection of all of the sets that you want to have this property, right? So look at how S bar is defined in 4. It says that S bar, let's say we actually defined S bar like this, right? Like I could have said the closure of S is the intersection of all the closed subsets, all the closed sets containing S. It is now automatically 3 is true, right? Namely to say, if you give me any other closed set, S bar must be in it, right? Because by definition of 4, it is the intersection of all those things. So it must automatically be a subset of it. If C is, right. Okay, so maybe that's not maybe that's not what he meant. Okay, so if C is closed and S is subset of B, then S bar is subset of, right. Okay, so here is what we're using for this one. Right? So if A is a subset of B, then A bar is a subset of B bar, right? And so in 3, what I'm using is I'm going to apply that as if this is A and B, right? And so that means that the closure of S must be contained in the closure of C, right? So that's what I've written here. The closure of S is contained in the closure of C. And then C is closed. So by the previous one, right? We said that S is closed if and only if it's E. Okay, perfect. And Ty, yes. So you have to think about it. I did say that 3 and 4 are equivalent, and they are, and you do have to think about it a little bit, but convince yourself. So again, we used 3 in order to prove 4, right? So 3 implies 4, right? We get that for free. You need to convince yourself that 4 implies 3. So even though I didn't use property 4 to prove property 3, suppose that you knew that property 4 was true and property 3 is not true, and convince yourself that you immediately get that property 3 is true. Does that make sense? So you want to prove for these two statements to be equivalent, right? You want to show 3 if and only if 4. And we've already done 3 implies 4, right? We use that. Convince yourself that 4 implies 3. It's very, very quick, right? So convince yourself, if you know that 4 is true, you can prove that 3 is true. So if you want, if you can somehow find a way of proving 4 without using 3, then you can immediately get that 3 is true. And therefore, these statements are equivalent. Okay. And like I said, some people actually use property number 4 there as the definition of the closure, in which case number 3 is just an immediate consequence of that. So that's the sort of idea there. But that's this common trick. Okay. So in mathematics, let's say you want the smallest set which does something. So one of the things that you can do is say, take all of the sets which satisfy that property and intersect them. Do you know what I mean? And depending on, what property you're trying to preserve, what you get should be the smallest set which does it. So in this case, what we were trying to do is we were trying to find the smallest closed set that contained S, right? That was kind of the property that I wanted to preserve. So I defined K as the collection of all sets which do that, right? All closed sets which contain S. And then I take their intersection, and reasonably speaking, their intersection should still have that property. You have to prove it, but the intersection should still have that property and would therefore be the smallest thing that could possibly work, right? So that's a math trick for how you get around and how you find the smallest thing which does something that you want it to do. Okay. So those are some nice facts. And anytime you're trying to prove stuff about, like, basically, look at what this proposition does for you. If you want to show that a set is closed now, you know a ton of things. You can show that it's equal to its closure. You can play around with the closure. Basically, you don't have to think about openness to prove closedness, right? That's the idea of this proposition. It gives you an entire toolbox so that you can completely avoid having to show that anything is open. If you actually want to show that things are closed, right? So if you want to show that something is closed, you can skip now showing that its complement is open, because we have a fairly extensive toolbox that just deals with things like the closure and the boundary points and things like that, right? So that's kind of nice. That's what this all does for us. It kind of sets us up for that. Okay. All right, I am now officially going to do everyone's favorite theorem. So I think I've done this now in office hours, and I think at least one of the TAs did this in the tutorial, which is to restate continuity in terms of open sets. Okay, and so here's how this goes. Note that the epsilon delta definition what do I want to say here? F is continuous at a point A if, okay, so first thing, let's just write down our classic, everyone's favorite. I know, I said that sarcastically. Okay, so for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in R, x minus c less than delta. Okay, so I'm just writing the classic definition, the one that we all know and love. Like that. Okay, so now we can translate this to balls, because I said, right, the absolute value of x minus c being less than delta is a statement about being in a delta ball, right? So now if I rewrite this as in the ball notation, this is going to say for every x in B delta C, f of x, or let's say, yeah, f of x is in B epsilon f of C. Okay, so I want you to stare at that for a second and convince yourself that it's true. Right? And so again, I've kind of like merged some things, but the statement for every x in R, the absolute value of x minus c being less than delta, is saying, let's just look at the x's which are satisfy x minus c is less than delta, i.e. let's look at those points that are in the delta ball around C. And if I know that x is in the delta ball around C, then the implication is that f of x must be in the epsilon ball of f of C. Okay, and so if you wanted to, you could state this as well as if x is in B delta C, then, right? Because we know that for all statements and if then statements are very closely related. Like that, right? If x is in the delta ball, then f of x is in the epsilon ball. Okay, so immediately, very nicely, we do have, when you phrase things in terms of the balls, they're very, very nice. And we can go one step further. If we are willing to use images, for every epsilon, there exists a delta greater than 0, such that f of the delta ball around C is contained in the epsilon ball around f of C. Okay, that one requires a little bit more thinking, but what are we saying? We're saying if I start with an x and then I take f of it, right? So if I start with an x in the delta ball and I take f of it, then I get an element of the epsilon ball. right? That's exactly what this statement is saying. It says that if you choose any x in here, then f of it is in here. Okay, so as a statement on balls, on like epsilon and delta balls, you are continuous at A if for every epsilon ball, you can find a delta ball which maps into it. Okay? Does that make sense? And so maybe like we can kind of draw a picture here. So if we think of this as being the real numbers, and this as being the real numbers, okay, and F maps numbers on the left-hand side to the right-hand side, let's maybe say this is our point A here, and maybe this is, or I guess I'm using C, so I should use C. So this here is F of C. So it says, you give me an epsilon ball over here. Oh man, I am gonna run out of space. I did not draw this big enough. Okay, then I can find a delta ball. Such that if I look at what F does to that, right, it's actually gonna map it inside here. And I know that this is not the picture that we normally use for epsilon and delta, right? We normally look at the graph of the function and look at epsilon and delta bands. But this is exactly what's happening if you try and think about, instead of visualizing a graph in terms, or a function in terms of its graph, you think of it as a machine, an input-output machine. This is exactly what's happening, right? This is exactly what is happening in terms of balls now. So this is an alternative perspective of continuity that doesn't use the graph, and this is actually superior. So the epsilon and delta definition is really nice when you're dealing with functions from R to R, and it gives a nice bit of graphical intuition that you can use. But the reality is that the moment you start dealing with functions that don't map R to R, and you can imagine most functions don't, right? Most functions in real life and in mathematics do not map R to R. They are much more complicated than that. It becomes intractable to think about the graphs, right? If I give you a map from R3 to R3, the graph of that thing lives in R6. You're probably not going to visualize things in terms of epsilon and delta, but you can still think of a map from R3 to R3 as something which takes a point in three-dimensional space and sends it to another point in three-dimensional space, right? That is still a valid picture of a graph or of a function. And so having this notion of balls and saying, look, if you give me an epsilon ball around the point, F of C, can I find a delta ball in my domain which maps to it? That is a much better picture of continuity. Usually we don't give it to first years. We require a little bit of mathematical maturity in order to really present this picture, but this is a much better picture. How to spell B? What do you mean? Like it's just called the open ball, right? This is just called like a open ball of radius R. I heard in RN they define the ball by distance function. Yeah, exactly. So if you come take 257 with me, we will basically what we do is repeat first year calculus in 6 weeks, or first year differential calculus in like, oh no, I guess we take the entire term to do it. But basically we'll redo all of this, but we change what the notion of distance means, right? So right now here implicitly, we've always been using the Euclidean distance, right? This is the Euclidean distance thing right here. Here's where it's showing up, right? The absolute value of x minus c being less than delta is our usual notion of distance, right? Where I say, oh, how far away is -7 from +10? It should be 17 away, right? And yeah, if you take the absolute value of -7 minus 10, you get 17. So this is our usual notion of Euclidean distance. And this is what I said, we were doing a special case of Euclidean topology. In 257, we will repeat all of this topological conversation, but we'll change what the distances are. We'll do it more abstractly, but there are just different distances that we could even use in R. And there are a few of them that we could use in R. So you can I don't want to get too much into that because it's really going to change things and make them a little bit more complicated. But yeah, you can change how you measure distance. And a lot of these things are still true. Okay, so let me state this. We're going to take our break here in a second, but let me state the theorem that I want to use. And again, you've probably seen it in the exercise questions in like the bonus assignment. I don't remember what assignment it was, assignment 4 or assignment 5, whatever it was. And then I think Alberto at the very least did it in tutorial. And the theorem is the following. So the theorem so a function, I'm just going to write R to R, but of course you can restrict the domain if you want, is continuous. And I'm going to just say continuous period, not continuous at a point, but is continuous if and only if whenever U in R is open, F inverse of U is open. And that's not F inverse, right? That's the preimage. So what we often say is the continuous preimage of open sets is open. And often we're just even lazier and we just say preimage of open sets is open, right? So that's what the second half of this statement is. The preimage of open sets is open. And that is equivalent to continuity. In fact, you could define continuity in this way. And topologically, this is actually what you do. If you ever go and you take like a real topology course, the definition of continuity is that the preimage of open sets is open. Okay. Now in analysis, like we're doing, we use a different definition of continuity, but they are equivalent. They end up giving you exactly the same thing. So a function is continuous if and only if the preimage of an open set is open. Okay. So what we're going to do is we're going to take a break. Again, try and prove this if you want. I think even in tutorial, Alberto might have only proven one direction of this. We're going to prove both directions and show that these are really the same thing. These are absolutely equivalent. Okay, they are truly, truly the same thing. And like I said, give them a shot if you want. So let's take 10 minutes. I've got about 10:05. By the time I stop speaking, it'll be about 10:05. So we'll come back at 10:15 and we'll give this one a shot. I think this proof looks worse than it is. It is one of my favorite, but I remember not really liking it as an undergrad, but whatever. This is an important one, so you should know this one. Okay, so 10 minutes. And again, if you have any questions, throw them in the chat. I'll take care of them. Yeah, I'll see you in 10. All right, so we'll get started pretty quick here. Hold on, though. I just got an email from a student in another class. Okay. Yeah, so we're going to do this proof, and this is one of the proofs. Ironically, I think that a lot of the pictures that I draw in R, because that's where we're doing topology, because we're in R, I usually draw intervals. But the interesting thing is that these pictures are often actually much better suited to be drawn in multiple dimensions. And in multiple dimensions, the pictures are actually clearer, believe it or not. This is one of the cases where I think we actually lose something by drawing the pictures in R1. So I'm going to try and draw this picture here in R. But again, I think the picture is actually clearer if you draw it in multiple dimensions. That won't necessarily make sense to you, but it is just one of these things that is kind of unfortunately weird. Okay, so let's prove this then. Proof. And let's just prove the forward direction. It doesn't matter the order that we do them in. So a function is continuous. So we're going to assume that f is continuous and then show that the preimage of open sets is open, right? So suppose that f is continuous. Suppose that F is continuous. Okay, so we want to show that the preimage of open sets is open. So let's start with an open set in the codomain, right? So let U be an open set. Okay, and let's take the preimage of U. And consider the preimage of U. We want to show this is open. So we want to show that if I choose some point in here, it is an interior point. Namely, I can put a little ball around it, which stays entirely within the set, right? So fix some X in F inverse of U. Okay, let me try and draw the picture here. So this is just the setup. I haven't actually done any mathematics. I've just tried to unravel what it is that we wanted to do, right? Suppose that F is continuous. That's just a hypothesis. Let U be an open set and consider the preimage of U. That's again just our setup for trying to prove the second thing. Now let's actually choose a point and show that it is an interior point. All right, so from a drawing perspective, let's see if I can do this. So again, here's a copy, here's our domain. I guess I don't need to draw these like super far apart. Here's our codomain, and F is going to go like this. I've assumed that the function is continuous, and I've got this set U here. Let's draw U nice and big. And of course, it doesn't have to look like an interval, but I'm going to draw it like one. Okay, and then I'm going to look at its preimage. So its preimage, maybe it doesn't line up perfectly. Maybe its preimage looks something like this. Right, I want to show that this is open. So what I'm going to do is we're going to choose a point X in here. Then I'm going to look at F of X, which is in there. U is open, right? We know for sure that U is open. So that means that I can put a little ball around F of X. And the claim, what am I going to claim? So I want to show that I can put a ball around here. I'm going to look at F of X. That's open. Why do I feel like I don't want to take that ball back. Oh, no, yeah, sorry. Yeah, I'm going to put a ball around here. This is going to be an epsilon ball, right? What are we trying to use? We want to use exactly this fact right here, right? So I'm going to let that be my epsilon ball. So this is going to be B epsilon F of X. And the epsilon here is just, again, I'm not trying to show that this function is continuous. I know that it's continuous. I'm going to use epsilon. Normally we use R, but I'm going to use epsilon because I want you to see how it relates to continuity. Because that's an epsilon ball, I then know that there's a delta ball in here, B delta of X, which maps into there. And that's going to be the open ball, that B delta, right? In F inverse of U, that's the open ball that I'm looking for. So you can see we're constantly moving backwards and forwards, right? I chose some X in the preimage, and then I looked at F of X, I took an open ball around it, went back to the delta ball, and that's the delta ball that I want. So we're kind of constantly jumping between the domain and the codomain, right? So this is the picture. It's kind of like a movie. And if you just see a static picture, it doesn't really make sense, but hopefully you kind of like watched me draw it, and that's what we want to do. So I'm going to say fix some X in the preimage of U so that F of X is in U, right? That's what I said. So we started at X on the left, went to F of X on the right. Now we know that U is open. Now again, normally I would say there exists an R here, but for our purposes, we're going to call it epsilon, such that B epsilon F of X is entirely contained in the preimage, right? Since F is continuous, at X, there exists some delta greater than 0, such that F of B delta X is contained in that ball. But this is exactly what it means for B delta to be in the preimage, i.e. B delta of X is in the preimage. Well, I guess maybe I should say that a little bit more clearly. Is contained within B epsilon F of X, which is contained within U. That's therefore that is f b delta of x is contained in the preimage of f of u, right? Because again, you have to think about it. What does the preimage of u mean? It means it's, you're in the preimage if f of u is in u, right? So if this statement here, b delta of x being in the preimage, means that if I take f of this, I end up in here, right? That's what the preimage means. And that's exactly what I wrote above here, right? So that's what that means. So that's what we wanted to do. So thus we found an open ball around x, which stays entirely in f inverse of u. Therefore, x is an interior point. Therefore, u is f inverse of u is open, or the preimage of u is open. Is open like that. Okay. So that takes care of that direction. In the opposite direction, we're going to do something similar. Is the picture here going to be worthwhile? So let me think. We have a preimage of open set. We're going to choose an epsilon. We're going to take the preimage of that. It's basically the same picture, I think. Just you've kind of changed what you're dealing with. Here, let me start writing it out. So we're going to suppose that the preimage of open sets is open. So suppose u open implies that f inverse of u is open. Okay. And we want to show that we're continuous at every point, right? So we're going to say fix some, I guess I'll call it C in R, and look at f of C. Okay. Fix some epsilon greater than 0, right? Our usual thing, we're trying to prove it's continuous. So what are we going to do? We're going to say fix some epsilon greater than 0. Or I guess our usual phrase is let epsilon greater than 0 be given. And take the epsilon ball around f of x. Okay, so you notice so far, for f of c, you notice that so far I haven't used anything about openness, right? There's been no open statement whatsoever. I've just said, let's set up our epsilon delta proof, let epsilon greater than 0 be given, and let's choose the epsilon ball around f of c. Well, that's an open set. And so its preimage must be open, right? This set is open. And remember, we're in the case where we've supposed that the preimage of open sets are open. So f inverse b epsilon f of c is open. And in particular, c is in there. Okay, so since this set is open, we can find a delta ball that entirely stays in there. There exists a delta greater than 0 such that b delta c is entirely contained in the preimage of the epsilon ball around f of c. And that's the same thing as saying that the image of the delta ball is contained in the epsilon ball. Right? And so we're done. So f is continuous at C. Okay. Any questions? I think this is a pretty nice thing. In fact, one thing that I think people take for granted, you'd be like, okay, I guess this is nice. We've learned that these are like equivalent things, but this immediately lets you prove that a lot of things are open. Because basically a lot of things are preimages of open sets under continuous maps. All right, I'm trying to think of, it's kind of, again, this is something that's definitely more interesting Yeah, more interesting in multiple dimensions, but is there kind of like an interesting, oh, okay. You remember the other day somebody was asking, actually in office hours yesterday, someone was like, hey, can you tell us what the term test question was? And the term test question from way back when, 2 years ago, was just show that 0, 1 is open, right? So for, let's say, for example, I guess zoom in a little bit again. So for example, show that okay. Now, first of all, what you could do is you could say this is an open ball, right? This is the open ball of radius 1/2, centered at 1/2. But actually, we haven't even proved that open balls are open. So you might want to do that at some point. But if I wanted to show that this set is open, what I could just say is something like this. I need a function. No, this is, no, I kind of need to use the fact that open balls are open for this. And there isn't a good example for this. I need multiple dimensions to really show you why this example is cool. So maybe not. Or I have to be a little bit more creative and think, is there a set that's actually really hard to show as open? Is there a set that's hard to show as open? It's not just like some sort of union of balls. At least that we could write down. Now I'm gonna have to think about it a little bit more. Just in R, there's not a lot of nice examples. Yeah, I'll have to think about this a little bit more. Yeah, I mean, like, so if I were to, I could draw it in RN and kind of give you examples of it in RN, but I mean, we haven't done the math for me to show you the example in RN, if that makes sense. Like, because what I was going to do is I needed that open balls were open in order to prove that 0, 1 worked. But if you know that open balls are open, then you don't need to use that, like 0, 1 is an open ball. You know what I mean? So it was kind of silly like that. But I guess actually, you know what? Maybe we could just try and prove that open balls are open. Sure, let's prove open balls are open. Even though I used it in this proof, so I really can't, I don't think I can do that, right? That's circular. But let me just do it as kind of an example to show you how you would use it, okay? So this is a circular proof, strictly speaking, because I did use that open balls are open. You would normally just prove that from scratch. But let's say, for example, let's say show that BR0 is open, right? And this is just the interval negative R to R. Okay, and the way that I would do this is to say define F mapping R to R by F of X is equal to the absolute value of X, right? This map is continuous. Is continuous. Okay, moreover, BR0 is the pre-image of negative infinity to R. And this thing is open. So BR0 is open. You see what I mean? That's kind of silly. Like, I need the fact that this interval is open in order to prove that negative R to R is open. But whatever, it is what it is. So you would do something like this. In multiple dimensions, this is a much more interesting question. Here, it's not as much because I can't create weird exotic shapes. There's just not enough dimensions to move around. Okay. Okay, everyone take a second, catch your breath. Because the next part is where it starts to get real. But This is one of my most favorite subject. I remember, again, being an undergrad and not really appreciating how awesome this subject was and kind of hating it the first time I saw it. But the more I saw it, the more at least it is still, that's right. Yeah, it's about to get real, but it's still real. No, yeah, the first time I saw this subject, I think I didn't really, I was intimidated by it, but the more I played with it, I was like, oh, okay, this isn't bad. And this is actually really, really nice. So, but I think it's going to look scary. And if it doesn't look scary, that's phenomenal. Okay, so definition, fix a set S, or let's say if S is a set, a cover of S is a collection of sets. Let's, no, I'm going to draw it scripty O because I can actually draw those. Is a collection O of sets such that S is contained in the union of those sets. Okay, so that's what a cover is. Now, more detail. So we say O is an open cover. If every element of O is open. We say it's a finite cover if O has only finitely many sets in it. And remember, O is a set of sets, right? It's a collection of sets. We say that, maybe let's use P, is a subcover if S is still contained in the union over P. Okay. Is S a cover of S? Yes. Yeah, it is a single cover of the set. Yeah, so good question. I guess actually I wouldn't write that. So Sultan, we have to be a little bit more careful. I'd say S is a cover of S. Right? The set containing the set S is a cover of S. So S by itself isn't, because a cover has to be a set of sets, but the set of S is a cover for S. If that makes sense. Hopefully it does. Yeah, it seems like some sort of pedantic thing, but yeah, it's absolutely true. Well, a subcover still has to cover your set, right? Like it still needs to be such that when you take the union over everything in it, that you still cover your set. So generally the empty set won't be a subcover unless the set that you're covering in the first place is the empty set, right? Like that generally won't work. And then everything is a cover of the empty set. So here, let's do an example. Yeah, P is just a subset of O, right? It is just a collection. It is a sub-collection of the covering sets. So again, this is kind of like freaky because again, we're talking about sets of sets and these sorts of things, but let's do an example and try and cement it. So let's say, for example, okay, let's let S be 0, 1. Okay, so for example, we could do something like this. Let's call this O1. And I'm going to let this be the set of sets of the form N. No, let's do N over 2, N plus 1 over 2. So where N is any integer is a cover. Okay, you can see it's a really inefficient cover. In fact, this is a cover for any subset of the real numbers, right? This eventually enumerates every possible real number, but it's still a cover, right? If you take the union of over O1, you get the real numbers, and that definitely, contains S. So yeah, that's definitely a cover. We could do something like this. It's not an open cover though, right? Notice that the sets in there aren't open. We could do something like O2. let's take n plus 2, where n is an integer. This is an open cover. Again, it's an open cover for actually any set. Right? Let's take p to be what? I want -1, 1, 0, 2. This is a finite subcover, a finite open subcover of O2. It's a finite, right, so that's the open cover. This is a finite open subcover of O2. We could take like O3 to be, and so far everything here has been kind of countable, right? But we could definitely do uncountable. So let's take the open balls of radius 1/10 at x, where x is in, let's say 0. Let's maybe take open 0, 1. Okay, so you notice O3 has actually uncountably many elements in it, right? O3 has uncountably many balls because we've taken the ball of radius 1/10 for every element in 0, 1. And yeah, there's a lot of redundancy in here, right? It's like really, really inefficient. And in fact, O3 itself will also admit a finite subcover, right? But there's no restriction on the number of elements that have to be in your covering set. They could be finite, they could be countably infinite, they could be uncountable, they could be really, 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 there could be a lot of such elements, right? But these are all examples of covers of the set 0, 1. Okay? Are there any questions? You're looking for a collection of sets such that when you union together all of the sets, you cover your S, right? That's what we mean by a cover, right? Just the union of them together is bigger than S. Okay. So our goal here, what we're basically, maybe let me, before I do this definition, maybe I should tell you what the goal is, because otherwise this is just going to come out of nowhere. So our goal is we want to capture the specialness, which is a weird word, but the specialness of the closed interval AB. Okay, because the closed interval AB is super, super important. If, for example, it shows up in the extreme value theorem, right? And I said when we were talking about the extreme value theorem, this needs to be a closed and bounded interval, right? Same thing, when we said if f is continuous on the closed and bounded interval AB, then it's uniformly continuous, right? We did that proof as well. So what we found is that there were a couple of cases where this interval, which was closed and bounded, was absolutely critical to our proof. So continuous functions on a set of this form are uniformly continuous. The extreme value theorem holds. So if I give you a continuous function on a set of this form, it's guaranteed to have its max and min, things along these lines, right? So what we want is we want to capture the specialness of this, but maybe we don't need it to be quite as restrictive as this. Maybe we can be a little bit more general than this. So I'm going to give you the full definition. And the full definition is, well, let me write it out. But basically, I'm going to explain to you the history of this, because you might be like, well, this seems unnecessarily complicated. And I would say that's a fair statement. So I said S is compact if whenever O is an open cover. Okay, it has to be an open cover. This is important. So S is compact if whenever O is an open cover, you can find a finite subcover. And the word that we use for that is often admits. So we'll often say O admits a finite subcover. Okay, so a set is compact if every open cover admits a finite subcover. So you can find, right, no matter what open cover you give me, in fact, I could have covered it by only finitely many elements of your cover, right? So it doesn't matter how crazy big you give me. You give me something like O3, which is gigantic, right? In that blue example above, you give me O3, which has a crazy number of sets in it. And I say, well, actually, the majority of those sets are useless and redundant. I could have done it with only finitely many of those sets, right? So a set is compact precisely when every open cover admits a finite subcover. All right. Now this is crazy because you're just like, well, you set our goal. So R and Q are not compact. Precisely. Yeah, R and Q are definitely not compact. And you might say, well, like our goal was to capture the specialness of AB. I don't, what, like, how is this that, right? How is that the same thing? So kind of historically, here's what happened. The special thing about the set AB is that it is both closed, right? It is a closed set. I think we all agree with that. And it contains all of its boundary points. So it's closed and it's also bounded, right? It doesn't shoot off to infinity in either direction. So it's closed and bounded. So historically, originally, that was the definition of compact. You were compact if and only if you were closed and bounded, okay? So that was the historical definition of compactness. And then what we realized is that that actually doesn't quite do it, for the reason that this doesn't generalize well to other spaces. So when you go and you start doing, and as we were talking about, in 257, for example, we'll talk about different ways of measuring distances. And we'll talk about R2 and R3 and Rn and infinite dimensional spaces and things like this. Closed and bounded doesn't cut it. The specialness of AB is not, in fact, that it is closed and bounded. The correct definition of compactness is that every open cover admits a finite subcover. However, in R, those are the same thing. Okay, so I will prove one of these directions for you, but I do kind of want, it doesn't, well, what is the definition in my textbook? What's the one that I use? Do I use closed and bounded? Right. And because, again, so I'm showing you this one because this is the correct one, because I didn't want to state and prove Heine-Borel. I am going to state this for you now, and I will probably prove one direction of this later. But here's the following statement. This is called the Heine-Borel theorem. So a set is compact. A set S in Euclidean R, which we're not going to say because everything for us is Euclidean R. A set S in Euclidean R is compact if and only if it is closed and bounded. Okay. So there is value in doing this, and I must believe it because apparently I used it in my book, of defining a set to be compact precisely if it's closed and bounded. And if the only thing you're doing is working in Euclidean R, then that is a perfectly fine definition because Heine-Borel says these are the same thing. Saying that every cover admits a finite subcover is the same as saying that you are closed and bounded, okay? However, again, the reason I want to give you the open cover definition is that if you go and you do any mathematics, any more advanced mathematics, this is the definition of compactness. This is the correct definition of compactness. And you have to use this one because the moment you leave Euclidean R, this is like closed and bounded does not cut it anymore, right? It just does not work. So this is the correct definition. But if you're only going to work in Euclidean R, closed and bounded is fine, okay? So, do I want to do this yet? I mean, I could, am I at a stage where I could just prove this? Let me double check. Because I hadn't planned on doing it until later. Okay, I think I could just prove one direction for you, i.e. I can prove the forward direction. So I might as well just do it now, whatever. The opposite direction we don't yet have the tools for. I need sequences, and we're not going to do sequences until like February. So in February, you can remind me and I'll prove the other direction for you, but I need sequences in order to be able to do it, okay? There might be a non-sequenced way of doing it. I haven't thought about it. But the easiest way is definitely with sequences. So yeah, remind me in like February and I'll do the opposite direction for you. Okay, so proof, we're only going to do this one. So if you are compact, then you are closed and bounded. So suppose S is compact. Okay, so again, remember what we're assuming. We're assuming every open cover has a finite subcover. So I want it, let's show that it's bounded. This is the easy proof. So what I'm going to do is I'm going to let O be Bn0, where n is in the naturals. Okay, so basically I'm just taking the intervals, you know, -1 to 1, -2 to 2, -3 to 3, -4 to 4, -5 to 5, etc. That's an open cover for my set because it's, again, it's going to cover, in fact, any set of real numbers. So this is an open cover. For S. Okay, so since S is compact, there must be a finite subcover. Is compact. There's a finite subcover. Cover, and we can just enumerate them, N1, NK, right? And all I'm going to do is just take the biggest of the NKs because all of these balls are nested inside of each other, right? -1 to 1 lives in -5 to 5, lives in -17 to 17. So these balls are all nested. So it's taking, let's say, capital N to be the max. And again, I need finiteness in order to be able to do this, right? We have that S is contained in the intersection from I equals 1 to K, Bn sub I of 0, but all of these balls are nested, so it's contained in Bn of 0, and so you're bounded, right? So S is bounded. Okay, so that was the easy one. Now for the tricky one. And there's definitely a couple ways of doing this one. I really like my proof, but you don't have to use this one. There's a couple others you could do. All right, so it goes like this. So for the sake of contradiction, let's suppose that you're compact but not closed. Contradiction. Suppose S is not, nope, what? Is not closed. Okay. So in particular, we can find a boundary point. Let's call it X. Maybe I'll call it X naught in the boundary of S that's not in S, right? And that's what, because we know not being closed means you have a boundary point that's not in your set. So now what I'm going to do is the following. I'm basically going to, and this proof actually works in Rn, the proof I'm about to give you. And actually the proof I give you for boundedness works in Rn as well. So this proof is actually going to work for all of Euclidean Rn, not just Euclidean Rn. So for every X in S, let R sub X be the absolute value from X to X naught divided by 2. Okay? Excuse me. So what I'm saying is, cough, hold on. Okay, so what I'm saying is for every point in the set, find the distance between X and X naught and divide that number by 2. And every single one of these is bigger than 0 because X naught is not in S, right? This is the important part. This is where I'm using the fact that X naught is not in S. Yes, you could think about it that way, sure. Like that's not, that does end up being true in R. Again, this kind of proof holds in general. So in that case, it's just half the distance between them. But in R, you're right, that is the midpoint. So you could totally think about it like that if you wanted to. So I'm going to let X be, or let R sub X be this sort of midpoint and define, I'm just going to call it Bx to be the ball of radius X centered at X. Okay. So the claim, this is an open cover. So note that these Bx's, where X is allowed to be any element of S, is an open cover. Do you believe that? Right? They're certainly open, right? Because each one of these things is an open set. And notice that every element of S is the midpoint, is the center point of this ball, right? Every element of your set is the X, which I'm unioning over. So it certainly covers every element of the set, right? So because the set is compact, there must be a finite subcover. And so there's a finite subcover. Let's say Bx1, Bxn. Now, hopefully see what the issue is. Every single one of these balls is far away, in some sense, is far away from X naught, right? Like none of them are nearby. I guaranteed that each of these balls, their radius was only half the distance to X, so to X naught. So how is this even going to be possible, right? It's not going to be possible. Something here has to break. So yeah, here, let me put it like this. So note, okay, so since X naught is in the boundary, or here, let's take, so let's let R be, what do I want? The min? Yeah, I probably want the min of Rx1 through Rxn, like so. Okay, so each of these balls, remember, corresponds to some radius. So I'm going to take the minimum of their radii, and then I'm going to say, look, well, that ball has to intersect S. And since X naught is in the boundary, we know that BR, well, let me put that on new line, BR of X naught intersect S is not empty. So let's pick an element in there. I'm going to call it X hat. B and BR X naught intersect S. Okay. Now, that element, because Bx1 through Bxn is a cover, it must be in one of them. So since Bx1 through Bxn covers S, we know that X hat is in Bxk for some K. Okay, and I claim this is a contradiction. This gives a contradiction. Since, okay, so what do we know? So we know that X hat is in Bxk. Right? So what does that mean? That means that the distance between Xk and X hat has to be less than Rk. Right? Did I want the max? Yeah, no, I think I'm still okay. Okay, what else do we know? We know that X hat is in BR of X naught, right? i.e. X hat minus X naught is less than R, which is itself less than Rk, right? Because R is the minimum of those things. Okay? So what that means then is thus, the absolute value of, which one do I want to take here? X hat to X what else do I know here? X naught to xk. Right, x naught minus xk. So we're going to use the triangle inequality here, x hat minus, oops, so x, what do I want to do? X naught minus xk, x naught minus x hat plus x hat minus, well, this is just equal, minus xk is less than or equal to, what I'm really doing here is just reproving the reverse triangle inequality, but I only wanted half the identity. So that's why I had to reprove it. Right? So that implies that x naught minus x hat, this thing is greater than or equal to x naught minus xk minus x hat minus xk, right? And x naught minus xk, this was greater than or equal to 2, do I want? Yeah, 2rk, right? Because rk itself is xk x naught minus xk over 2. This thing is going to be greater than rk. So I get greater than or equal to rk here. And that's a contradiction because if we look at x hat minus x naught, here I got that it's less than rk. And then here I got that it's bigger than rk. Right? And so S is closed. Does that make sense? And this is a hairy thing. By the way, remember, this is only the forward direction of this proof. This proof also has a backwards direction, and the backwards direction is harder. Yeah, I know, the cat's being very loud. So when I say this is a named theorem, right? This is the Heine-Borel theorem. It's because like it has a name because it's a big and nasty and important proof. And yeah, this was just the forward direction. The other direction is worse. So kind of keep that in mind, right? The proofs are kind of nasty, but we are only going to use kind of, right, for now, let's assume that this theorem is true, and I'll prove the other end for you, like I said, in February or so. But yeah, you can kind of assume that this is true for now. Okay? So that's the forward direction. On Thursday, I'll prove a couple more things about compact sets, which are very nice. For example, the image of a compact set, the continuous image of a compact set is always compact, turns out. So you can try to do that one if you want. Actually, that one's really, that's a fairly easy proof, but it's really, really beautiful. So let's say theorem, and I'm going to leave this as an exercise. You can try it. So if F maps R to R is continuous and K in R is compact, then F of K is compact. And you'll notice that this is different than openness, right? With the open, you took pre-images, and pre-images of open sets were compact under continuous functions, pre-images of open sets were open under continuous functions. Compactness is the opposite direction. Compactness is the image of compact sets is compact under continuous functions. Okay, so this proof is actually surprisingly easy. I would very strongly recommend that you try to do this. But for this one, when we say the word continuous here, you're going to use pre-image of open is open, right? Like don't use the epsilon delta definition, right? Because the definition of compactness is entirely defined in terms of open sets. Don't use the epsilon delta definition. But yeah, okay, so this is kind of how you want to do this. Give this one a shot. It turns out to be surprisingly straightforward and is a really nice, really fun exercise, and is in fact equivalent to the extreme value theorem. So once you've proven this, the extreme value theorem falls out immediately. And you don't have to do all that weird sort of forcing that we did way back in the day. So this is why some people actually, I think, do teach this definition of compactness, because you can just do the extreme value theorem much, much easier with this definition. Okay, everyone. So that's going to finish us off for today. I'm actually like a minute over. Yeah, so thanks very much for coming, and I'll see you on Thursday. And you have a test on Friday, so be ready for that too. All right, thanks everyone. See you later.